one of the best ways I know of to compare the flexibility of distributions is with this beta 1, beta 2 chart, which was developed back in the time of Carl Pearson to compare what is the range of skewness you can achieve with various distributions. And this beta 1 is the standardized skewness, that is the third central moment divided by the cube of the standard deviation, and you square that so you get a positive number. So as you go this way, distributions are more skewed. Distributions that are symmetric are all along this axis. This axis, beta 2, is the standardized kurtosis, and that's how fat are the tails, basically. So everything along this axis, as you go down here, has fatter and fatter tails, but it's always symmetric. So any distribution that has no shape parameters corresponds to a particular point on this chart. By the way, there's an area of this chart up here that is infeasible for any distribution, because basically, if you do not have very high levels, if you cannot get really high levels of skewness unless you also have relatively high levels of kurtosis. So there's an area of infeasibility for all distributions up here. But anyway, any distribution that has one shape or zero shape parameters, like a normal, it always has the same shape. You can make it wider or narrower, but it always has the same shape. It has a standardized kurtosis of 3, and that you can see there. Logistic distribution is 4.2. The uniform distribution is one of the shortest tail distributions. It's 1.8. And here, and for any distribution that has one shape parameter, which the triangular distribution does, there's the entire range of flexibility of the triangular distribution. You can go from here to here, but no more and no less, okay? Now, any distribution that has one shape parameter, like the log normal distribution, for example, it corresponds to a line on this chart. So there's the log normal, here's the gamma distribution, here's the inverse gamma. Any distribution that has two shape parameters corresponds to an area on this chart. So here's the beta distribution, for example. Beta distributions are relatively short-tailed distributions, but they correspond to a wide area range on this chart. Anything in this range corresponds to the F distribution, which also has two shape parameters. And then down in this range, you have the so-called Pearson 4 distribution, which is a very difficult distribution to deal with, which also has two shape parameters. Everything over here, as you go down this axis, you really have your student T distribution. So here's a student T with, with infinite infinite degrees of freedom, student T corresponds to a normal distribution. Here's 15 degrees of freedom, 7, 6, 5, 4. As soon as you get to 3, you've got a student T that has such fat tails, it's off the chart below this. And if you get to 1, you get the Cauchy distribution, which is so fat-tailed that it has no measure of either skewness or kurtosis or even a mean. So I give you all this background. Now, I also, just given our discussion of Weibull distributions, I thought it would be interesting to plot where's the Weibull distribution on this chart. Turns out it's right here. It's very much like the gamma distribution in terms of how fat its tails are. The Weibull with shape parameter of 1 goes right through the exponential distribution, which is located here. Okay, but it's a reasonable, I'd say moderate-tailed distribution with, of course, a lower bound associated with it. Now, so anyway, that's the chart on which we can now look at where's the shape flexibility of the Metalog system. Well, the 3-term Metalog that I just showed you, that range of shape flexibility goes from the logistic distribution exactly out here to about the exponential. So those most extreme 3-term Metalogs that I showed, the most skewed ones that I showed on either way, have a skewness and kurtosis that's very, very similar to that of the exponential distribution. So that's about what you can do with the 3-term Metalog, and you can do anything in between. You can have a symmetric 3-term Metalog, which of course corresponds to the logistic distribution exactly, and that's why you're on this line. Well, we're not going to talk about 4-term metalogs today. As soon as you go to a 4-term metalog, then you could have anything in this area here, which covers most of the range of an awful lot of practical distributions. And it doesn't cover these bounded distributions, but the 4-term logit metalog does.